And have our second speaker, that's Florian Haupt, and he talks to us about API governance support through structural analysis of REST APIs.
So, welcome. Thanks for the introduction. Already mentioned, my name is Florian Haupt. I'm from Frank's Group from Stuttgart. And so the topic today is API governance support, structural analysis of REST APIs. And during the talk, I will start from that. So I will first talk a little about REST APIs, so what is the structure of a REST API, so that we have a common understanding. Then talk a little bit about an analysis framework that we published before, that we reused in this work, and then about what we call the perceived complexity of REST APIs. So, the main motivation for our work is that there are many REST APIs out there. So, if you consider, for example, Google, they have like more than 100 public REST APIs. I don't know how many they have internally. If you think about microservice architectures, then we also have like many REST APIs. And our goal is that we somehow want to give like a high-level overview about big sets of REST APIs. To get some understanding about their characteristics and then to finally support people in API governance. So to understand big amounts of REST APIs. So this is the main motivation. And it's all about the structure of REST APIs. And now, what is the structure of REST APIs? It's somehow related to what is called paid loss. So just let me give a little introduction. So basically, the REST architectural style is defined as a set of constraints. You can consider them as rules that you have to fulfill to build a REST architecture. And one of these rules is the hypermedia is the engine of application state, which basically says that the server controls the state and the state transitions that a client can make. So basically, this is what you do every day when you're surfing a web page. So when you enter a web page, for example, this is the starting page from a blog, then you have a set of links on this web page. So for example, you decide, so now this blog post is interesting, then you can click on this heading, which then triggers the browser to fetch this page, and then the new page opens. So, and again, you have a set of links. So you're like surfing on the website, reading, maybe scrolling down, seeing the comments below the blog post, and you decide, okay, this guy said something very interesting, so maybe check him out. So again, there is a link which guides you to the next web page, which might be a totally different web page from a different provider, different host, whatever. So, and basically, these web pages and how they're connected by links, this is what we consider as the structure of an API. And you often see this on some web pages. They provide what they call a sitemap, which basically gives you the high-level overview of what is on this page and how can you navigate through. So this is what we consider as the structure of a REST API. The same applies for REST APIs that are not made for humans, but for machine-to-machine communication. So this is basically, the blog was on Google Blogger. They also provide a REST API for machine communication, where you basically can do the same. So you can get request to this URL, and then you get a JSON representation, basically describing the same block as we've seen before. And again, this representation contains links. So for example, this is now, you can pass through here and see, okay, now this is the link which will guide me to the list of all posts of this blog. So I can extract the link, do a second GET request, and then you get the representation of the list of all posts that this blog provides. And again, you can here find a link to a specific post that you may be interested in, can extract the link, issue a GET request, you get to the post, then you can, again, it links you to the list of all comments, and then, similar as in the example before, you can see, okay, now this is one specific comment, there's the author, and again, there's a link pointing to the page of the author. So basically, the same principle as we've seen before. Again, this REST API has a structure comprising the resources, so the endpoints it offers, and the links in between. And again, there might be more. And the visual notation that we will use in the rest of this talk is, as we've seen here, so this is from a modeling tool that we developed. Basically, the gray boxes are the resources of the REST API, and the colored boxes are the method that are supported by the resources. So, and the semantics here is basically that if you do a GET request in this resource, then the response offers you hyperlinks that allow you to navigate to this resource, this, and this resource. So this is how we describe the structure of a REST API. The resources, the methods that they offer, and the navigations that are possible between these resources. So now the title said something about analysis of REST APIs. And if you have a look at the related work, so there has been some work done on the analysis of REST APIs. And the first group of papers is about, it relies on human-readable API description. So usually for REST APIs today, you have like web pages that describe how to use the API and so on. So targeting for developers. And there are some works which basically take this description and do an analysis, a manual analysis, so people reading, analyzing, checking for certain attributes and so on. So this is one group of related work analysis. Of course, it's manual, so it might give meaningful insight, but it's also like doesn't scale for a huge set of APIs. So there's a second group. They rely on analyzing response messages that are exchanged between clients and REST APIs, and then they do an automated analysis. So like processing large amounts of messages, HTTP messages, and then analyzing them. So, and the approach that we took is different to these tools. What we rely on is that we assume that there's a machine-readable API description for REST API. So if you, for example, know Swagger, this is exactly what we use there. And these descriptions can, like, there are two use cases. Either you design the API, which is such a format, and then generate the REST API or the start of the implementation. Or what is also often done, like you have the implementation, put some annotations in the code, and then this description can be generated. But the most important part, it's machine readable. It's, for example, JSON or YAML or whatever. And so what we did, we analyzed these API description documents either in a manual way, like visualizing them with our tool, or in an automated way. So this is the approach that we took. And one advantage is here that what is great about this is that you can even do this analysis at design time. For this approach, you need like a real running API, so you need the messages to analyze. What we can do here is really we can design the API using one of these languages and then do the analysis before we really implement this. So, the most common API description language of this type is Swagger, or like has now been donated to the API Foundation. So basically, as of now, still like the last version of Swagger is identical to the current version of OpenAPI. So in this talk, it's like a synonym. So during next week, the new version will come out, and then it will more be the same. But this is now we consider like Swagger and following. So this is the UI that they provide, which basically shows the REST API here of a set of URLs and the methods that it supports. Now, we could have done our analysis based on Swagger because it's very common, well known, and used in industry and so on. But there are other languages out there. So, and we didn't want to like log into Swagger. And what we already had from previous work is, so we did some work about model-driven design, development of REST APIs, and part of this work we created some meta models for REST APIs. So, for example, this one was for like higher level modeling based on conversations. So this was a work together with Cesare. And there's another meta model which is like a basic model of, so here called atomic resource model, which describes the basic ingredients of REST API. And this is what we use in this work. So on the important part is shown here. Basically, it corresponds to the visual notation that we've seen before. Basically, the model says, the meta model says, REST API consists of a set of resources. The resources support some methods that then can enable relationships to other resources. And what we have seen before in the example was like navigation relationships, like navigation between different resources. But it's also possible, like doing a post because on one resource results in the creation of another resource. So this is why because of this creation relationship. So we decided to use this meta model, and what we then had to do is somehow transform the other meta models in our. And what you see here is like that they represent the structure of a REST API. So the resource and relationships between them in a more implicit way. So basically, when you look here, like you can derive the structure from analyzing the structure of the URLs, and then you see here, okay, like this is like an extension of this URL, so this is a sub-resource of this. So this is basically what we have to do, like analyzing the URLs that were given there, and then deriving this structure to have it explicitly in our meta. So, and then the title said, okay, we know now what the structure of the REST API, so we wanted to analyze the structure of the REST API. And this is now a short introduction to some work that we presented at this year's XAM, so a few months ago, which is an analysis framework that allows us to do this in an automated way, which basically looks like this. So what we have here is like a repository with REST APIs models, which are based on our atomic resource model from our previous work. And then we basically take all the existing languages and transform them in this method. So, and then the one type of analysis that we support is like the manual analysis based on the visual representation, like using our modeling tool. You can simply have a look at these APIs and then analyze them based on this. And the other part is that you can also like define metrics about these REST APIs and their structure, put them in a repository, and then we have an analysis component that automatically fetches all the models here and all the metrics here, and then executes them in an automated way, basically resulting in huge tables of data about your REST APIs, their structure, their characteristics. And so this basically gives us then like, we have reusable metrics, of course we use this common meta model, and then also comparable results. And so we tested this framework, we run some first analysis, and what we used for that is, so we used a public repository which has like 286, at the time we used Swagger description for REST APIs. And the nice thing is that these are real-world REST APIs, so not some artificial models. These are from well-known providers. They have APIs from Google, from Azure, whatever. So all the Swagger files describing the APIs. And then we run our first analysis with some basic metrics. So not much into detail, but a little bit here. For example, we counted the number of resources, which basically represents the size of an API. And what you see here, so there are APIs with a minimum of like only providing one resource, up to APIs that have 264 resources, so quite big. And if you here compare the mean value of around 20 and the median of around 9, which is an indicator that the distribution is rather uneven, which we'll see in a minute. And we also calculated other stuff, like for example, we had a look at the resources and which method they offers, and just counted the read-only resources. So read-only resources are resources that only support the get method. So you can like retrieve data from them, but you cannot delete them, you cannot update them, you cannot process any data using process orders. So this is what we named as read-only resources. We also counted like how many resources to propose, delete. We counted the number of routes, so how many resources are there without incoming links, and also like the depth of an API. So how many links can I follow before I add a leave resource? And now, if you have a look at the detailed numbers, for example, this graph shows like the size of APIs. So here you see it's grouped like steps of 5. And so, for example, here at the left, so the orange bar now, is like there are around 90 APIs that have size between 1 and 5 resources, so rather small APIs. Then it goes down here, but what you also see, there are still some APIs here. So here's 1 or 2, here's 1 or 2, and we even have like around 10 APIs that have a size between 111 and 270 APIs. So most here in a rather small part, but also some quite big APIs. And now when we had a look at the set of APIs that we analyzed, what we discovered is that there are like 2 notable subsets in this repository, and these are the lines here. There are like 105 APIs from Google and 39 from Azure. So, and as these are like quite big subsets from only one provider, we have a detailed look like maybe they have different characteristics like the overall set. We can see this here on using another metric. So this metrics basically shows us here on the x-axis like how many resources of an API are read-only resources. So on the left, you see like how many APIs of this set have a read-only share of less than 10%. So basically saying these are APIs where you can, at nearly any resource, do some data manipulation, deleting, updating, posting, whatever. And on the right side, you have like, these are all APIs where the amount of read-only resources is between 90 and 100%. So these APIs are like read-only APIs or nearly read-only APIs. So they offer a lot of resources where you can retrieve data, but only little resources where you can create or manipulate or delete data. And now, again, the orange bar represents the whole set of 286 API. What you see here, for example, it's here rather more or less 10%. And then there is here the peak of like 25% of all the APIs in the set are read-only or nearly read-only APIs. Okay, so this is the whole set. Now we have to look at the distinct subsets. And now, for example, the blue line here. The blue line is the set of Azure APIs, or the Azure Cloud Platform APIs. And what you see here, that they have around, in total, like 50% of all the APIs have a read-only share, only between 30 and 50%. So more than half of the API offers you the ability to create data, to manipulate whatever data, and only very little of the APIs are read-only APIs. And if you think about that, it's very obvious because they provide cloud services which allow you to like create VMs, delete VMs, create networks, whatever. So it's about manipulating data, creating data. It's not, they don't provide any information service where you can just go and fetch some information. And so this is the Azure APIs. So Google is saying here more like only very little read-only, but more like here. And then if you have a look at the yellow line, so the yellow line are all the other APIs, not Azure, not Google. And if you have a look here, it's like 50% of these APIs are read-only or nearly read-only. So totally, or a very different characteristic than this. And then when you have a look at the set, these are, yeah, services like weather forecast, access to some databases, whatever. So just information services. And okay, so we did that. And now what you see, have you seen before, is that these are rather basic metrics. You have to do a lot of interpretation to get some result from that. So what does it tell me? You maybe have to combine 2 or 3 metrics to understand what they basically mean. And when we think of API governance, then yeah, they're not that helpful as they are. So API governance is more or less about rule compliance. So you have some rules and you want to check if the APIs are compliant with rules. These rules might be about non-functional properties, about best practices that these APIs should support, about the quality of their documentation, whatever. And if we now think of the metrics that we have, then we somehow have to tackle this. We somehow have to go from these low-level metrics to more higher-level, possibly aggregated metrics that help us to like answer these or check these rule compliance. And this is what we wanted to do in this work, basically. And what we did specifically is that we had a look at the complexity of the API. And if you talk about complexity, you have to distinguish between 2 kinds of complexity. So there's one thing which is called the descriptive complexity, which is like the objective truth, how complex something really is. And then there's another one which is the perceived complexity. This is how complex things seem to be, how they are perceived by a user. Sometimes these are the same, sometimes they are very different. And the question that we wanted to answer in this work is like, how can we determine the perceived complexity of REST APIs in an automated way? So doing it manually is easy. I just ask you, how complex do you perceive this API? But we wanted to do an automated way to support API governance for huge sets of APIs. And so now a little quick overlook of what we did, so the whole process, and then we'll go into some details later. So basically we started with selecting a subset of APIs from our set of these 286, and then we showed them to a set of developers that had some experience with REST APIs and asked them to rank these APIs based on their complexity, how it was perceived by the developers. And we used here the AHP process, so the analytic hierarchy process, which supports exactly such kind of subjective rankings. And basically what the developers had to do is like a pairwise comparison of all the APIs and saying this is more complex than this and so on. And then in the end what we got was like a ranking according to the developer's perception of the complexity of the REST APIs. We had a set of developers, so we consolidated this into one ranking. So this is what we did on one side. On the other side, we defined a set of candidate metrics. For that, we then wanted to check if these metrics can like be used to describe this ranking that was the result of the developer story. So we defined a set of metrics. We put the metrics and the models in our analysis framework, calculated all the metrics, and what we get was then a set of, we had 5 metrics, so a set of 5 different rankings of these APIs according to these metrics. And then what we basically did, we checked these rankings that we calculated, the rankings from what the developer said, and then we compared them, and then we're able to say this one matrix more or less reflects the ranking of the user. So basically the idea was that we can then use this matrix later to calculate the perceived complexity of an API without doing this user search. So this is the whole process. Now some details for the single steps. So we asked a total 9 developers that had experience with design and implementation of REST APIs. And then we showed them all the APIs, so all the 10 APIs, pairwise. And basically asked them API 1, API 2, which one is more complex? And then they had to fill out this here in such a table, saying, for example, they said here A is more complex than B. And then they had to give more details on a scale from 1 to 9, where 1 basically says they are more or less same complex, and 9 was the other extreme, which then said A is much more complex than B. And yeah, this again, and the nice thing about this AHP process is that it doesn't only result in qualitative ranking, so basically it's saying us according to the developer, this API is the most complex, and this is the second most complex, and this is the third most complex, but it also gives us some quantitative data. So basically these are the numbers here, which basically tell us that this API is 11 and this is 12%, saying this API is more complex than this, but only a little complex. But then compared with this API with this here, these are 15 and 25, so there is a bigger difference in the perceived complexity. So this is what this paper's done. We did this with, again, as I said, with 9 developers. So these are the bars here so the rankings from all the developers, and then we put them all together in one. This is the line here, one consolidated ranking. And this is so the quantitative approach is what you see here, basically that these APIs are more or less perceived with the same complexity, where here is, compared to this, a rather big difference in the perceived complexity. So we don't only have this ranking who's first, who's second, but only what's the distance between the similar APIs. So this is what we got from the one side. And then we defined some metrics for the other side. So this was asking expert, so which might be candidates for this. And we started with 2 basic metrics. So the first metric is the number of resources, which the size of an API. And the second metric is called the biggest component coverage. Let me explain this on this example. So this is one API. So again, this is the Globber API. And the biggest component coverage is when you see this API, it has 3 distinct subsets. So disconnected subgraphs. And this metric basically tells you, if you consider the biggest subgraph, which amount of the total API does it cover. So for example, in this example, this is the biggest subgraph of the API, and it covers, I think, 75% of the whole API. So this is what the second metric tells us. And then we took this 2 base metrics and composed some aggregate metrics from them, basically as M3 was then defined as M1 plus M2, then M1 plus M2 squared, and M1 squared plus M2. And of course, we then always normalize these metrics to have them comparable. So these were the 5 candidates. And then we used our analysis framework and calculated all the metrics, and this is the result that we get. So the black one here is the user ranking, and the other ones are the rankings according to the different metrics. So now the question is, okay, all the metrics resulted in different rankings, but which one now reflects the perceived complexity according to the users now best? And there are 2 ways how you can answer this question. So the first answer is if you're only interested in the qualitative ranking, so who is first, who is second, who is third, then according to this, you would basically say, okay, so then the best candidates are here, the blue and the gray, because same as the user ranking, they are here constantly rising, so the one that is ranked first is also ranked first for the user ranking, the second is the second, and so on. Okay. And now if you say, okay, but yeah, there's a rather high deviation in the value that is calculated here. So yes, it is ranked the most complex, but with a much higher value. If you say, I'm also interested in quantitative aspect, then what we did is basically then you can calculate the deviation from these metrics to the user ranking. And so this is what this graph shows. So basically we calculated the mean square deviation from the user ranking to the calculated rankings. And according to this, then the metric M3, so the purple line here is the one that deviates least from the user ranking. But as you see here, it results in a different qualitative ranking. So it ranks this API more complex than this, also the user will be different. So it depends on what you choose. So basically, that was an overview about the work. As a short recap, so first, it was all about the structure of a REST API. I showed what we understand as the structure of a REST API and how this is represented in other models, and that we have to do a little bit of transformation to really show it explicitly. We use an analysis framework that we have presented before, and then this was the overall process of the one hand asking developers for a ranking, and then on the one hand trying to assess some candidate metrics if they can represent the same ranking as the developer said. And we also have seen some details like the metrics of the use and so on. Thank you.
Thank you. Questions?
Developers is not too much.
Yeah, exactly.
You stole my
So no, it might be interesting to rerun this with more developers and of course. So we want to go for 10 with the one that
also judging, and this is not really related to present, but judging the evaluation of the artifacts. So if there are work done to let's say to analyze the probability of developers to rank the same object with similar values or different values based on the probability of just being random selection. So it reminds me of Cohen's kappa coefficient. That it's a different way. It cannot be applied here because it's for categories. But it's the idea that when people rank objects, they would have certain probabilities of just ranking them the same value for some random chance. And this type of metrics account for this. So, what are your thoughts on that?
I'm not sure if I got you right, but I mean, of course, what in any case is a thing that we might check again, or what you have to also consider is like when asking developers, it's also like a very subjective way. Even the representation, how we show them this stuff, might influence the results. So we try to do first step to see if it works anyhow, but
how sensitive are the results to your visualization? Because that's what you show the developers to compare. So do you think that showing them, for example, the human readable HTML
I think yes. So for example, we could, I mean, Swagger in the end is only a JSON file. So we could have shown them two JSON files asking which one is complex, but then it's more or less about, yes, it's then not about the REST API anymore. It's about like how you write the JSON file and so on. But of course, it depends. Like also, like Swagger has a visualization, like showing these URLs, and there's even no ordering defined. Right? Like showing them the same API only with a different ordering might reflect somehow the judgment of the complexity. So we try to keep the representation like uniform, so the way how we lay out the APIs to do the same for all the APIs. So not to introduce any side effects of this, but it clearly depends on the visualization, of course. But the idea was that more or less the visualization shows what we are interested in. It shows the structure in terms of like distributions. So this is why we're like confident that there is some relationship between the judgment from the developers to what we are really interested in, so the complexity of the API.
Have you considered giving them some understanding tasks, like being able to ask some questions about the API and then using your visualization to be able to answer?
Yeah, this would then be not the perceived complexity, but more the subjective complexity. So this is then when you're interested in sort of perceived complexity, it's really like how do people perceive it. And as I said, it might be very different to the subjective complexity, but to measure the subjective complexity is more complex. So, but then the way would be to like asking the developers questions about the API, asking them to do some task and check how long they need. So this would then be the step to going for the subjective complexity of the API, but then would be much more than only asking them, what do you think, which one is more complex. But yeah, it might also be, of course, interesting to check that and then at the end compare these two things.
Like a company could use a tool and check if their APIs, how complex they are. But if they find out any company, for example, it's very complex API and very difficult, what should you do? Should you what's the goal? Is it to reduce the complexity, to change it, or to make more APIs? So divide them in tools?
Yeah, I mean, it depends on the domain. So the basic idea is that we only provide the tooling. And then it depends, I mean, if you think about compliance, it's always that you have some business goals, and then you have to like push them down to some more lower level compliance rules that you then somehow have to check and ensure that they are really followed. And so this depends absolutely on that. But if a company, for example, says, we want to keep our APIs simple and small, for what reason ever, so for faster adoption or whatever, then they can use this. And of course, if they find an API that is too big and too complex, they have to look in their domain logic, what can we do? Maybe sometimes you can't do anything for it's like this, you can't cut it into APIs, but maybe sometimes it helps to just identify the points where you should.
Did you think about clustering your APIs? Because if you have something to manage a grid system or a cloud system, we have this objective truth. It is much more complicated. It has to be much more complicated than simply following the tree in the block structure. So comparing these both doesn't really make sense. You should make a first analysis as a cluster them towards their direction, what they want to achieve, and then you may can the cloud API from Azure with one from Google. That's okay to compare, but compared with the block, does it make sense at all?
Exactly. Yes. So. I mean, yeah, you're right.
Some classes of APIs.
Yeah, so usually, I mean, when you apply this in a company, whatever, you have more homogeneous, at least from the domain logic, more homogeneous APIs than we had in this set. But the nice of this set were really like real-world running APIs that are used out there, and that's some artificial sets that where you don't know if it's really meaningful what comes out. So it's just like.
More questions? Thank again both speakers. Shouldn't have killed it. For asking you, I powered it down. Makes no sense at all.